Welcome to Chapter 10 on Random Forests, XGBoost, and Ensemble Learning. In this chapter, we explore how combining many models can produce predictions that are far stronger than any single model on its own. If you have ever sat on a quiz team, you already understand the central idea of this chapter. A group pooling many imperfect opinions often outperforms even its smartest member. That is the promise of ensemble learning. By the end of this chapter, you should be able to explain the basic idea of ensemble learning and why it works. Distinguish bagging from boosting and say when each fits. Explain how random forests improve on a single tree, and describe bootstrap sampling and random feature selection. You should also be able to explain the intuition behind gradient boosting and what the learning rate controls, say why XGBoost is so effective on tabular data, train both random forest and XGBoost models in Python, and interpret feature importance carefully, aware of its pitfalls. This figure shows a random forest at work. Each tree trains on its own bootstrap sample using a random subset of features, and the forest then aggregates their predictions by majority vote for classification or by averaging for regression. It captures the whole idea in one picture. So, what is ensemble learning? It combines several models into one final prediction. In machine learning, the base models are usually decision trees, and their predictions are combined by voting, by averaging, or by sequential correction. Over this chapter, we will build up 5 connected ideas: bagging, random forests, boosting, gradient boosting, and finally XGBoost. Each one builds naturally on the one before it. These approaches dominate practical work on structured tabular data, the spreadsheets and database tables that make up so much of real-world machine learning. This is exactly where ensembles shine. Bagging follows 3 simple steps. Create many bootstrap samples from the training data, train one model on each sample, and then combine all of their predictions into a single answer. A bootstrap sample is drawn by picking observations from the training set at random with replacement. The sample is the same size as the original, but some rows appear more than once while others are left out entirely. Let us make this precise. A bootstrap sample has the same number of rows as the original, yet it contains duplicates and omits roughly a third of the data. Training each model on its own bootstrap sample is exactly what makes bagged models differ from one another. Bagging pays off most for models that are individually high variance, and the deep decision tree is the classic example. On its own, it is unstable, but it becomes excellent raw material once you average many of them together. A random forest is simply bagging applied to decision trees with one clever addition. At each split, the tree may only consider a random subset of the features. That second source of randomness is the key. The forest then votes or averages and usually trounces a single tree. It is worth being precise about why this works. Pulling many diverse trees cancels out their individual errors and curbs overfitting. But a word of caution keeps us honest. Random forests are more robust, not invincible. A handful of settings shape a random forest. The number of trees adds stability at the cost of computation, and returns flatten out, so a few hundred is plenty. Maximum depth controls how deep each tree grows, and minimum samples per leaf sets a floor on how many observations a leaf must hold. Maximum features sets how many features each split may consider. The dial that controls tree diversity, and the bootstrap setting decides whether sampling is used at all. A pleasant property is that forests are forgiving. They often work well out of the box and are less fussy than XGBoost. Like single trees, random forests can report feature importance, a measure of how useful each feature was for prediction. These scores can flag influential variables, though as we will see, they must be read with care. Boosting takes a different path. In 5 steps, train a weak model, find where it makes mistakes, train the next model to concentrate on those mistakes, repeat by adding models one at a time, and finally combine them all into a single strong predictor. A weak learner is a model only slightly better than guessing. Shallow decision trees, sometimes just 1 or 2 levels deep, are the usual choice here. Gradient boosting is the most popular form of boosting. For classification, the mathematics is more involved, but the spirit is identical. Every new tree moves the current predictions in a better direction. Gradient boosting has a few key knobs: the number of trees, the learning rate, the maximum depth of each tree, the subsample ratio, and the minimum samples per leaf. The learning rate deserves special mention. It controls how big a step each new tree takes, trading speed against the risk of overshooting. This sequential residual correcting loop is the defining contrast with the parallel voting of a random forest. This figure shows gradient boosting building its ensemble one tree at a time. Tree 1, then tree 2, and so on, each fitted to the current residuals and added in, so the final prediction is a sum of all the trees. It makes the sequential nature vivid. Gradient boosting can feel mysterious until you watch the residuals shrink with your own eyes. So let us work a tiny example. An ice cream stand wants to predict its daily sales from the day's temperature. We have 6 days of ice cream sales. Cool days sell about 20 units, hot days about 100. We will let gradient boosting discover this gap one small tree at a time. Gradient boosting builds the prediction as a running sum. We start with a constant guess, then repeatedly fit a small tree to the current errors, the residuals, and add a fraction of it to the running prediction. This is the rule we follow. Each residual is the true value minus the current prediction, and the new model adds a small fraction of a fresh tree fitted to those residuals. 2 short equations capture the entire procedure. For our example, we will use shallow stumps, each just a single split on temperature and a learning rate of 0.5. Round 0 is the starting guess. With no trees yet, the best constant prediction is simply the average of all the sales, which works out to 60 units. Every later tree only corrects this baseline. In rounds 2 and 3, we repeat the exact same step on the new, smaller residuals. The procedure never changes, only the errors it is chasing get smaller. This table tracks the ensemble's predictions and worst residual after each round. Every tree closes half the remaining gap, so the predictions creep steadily toward the true group levels of 20 and 100. 3 lessons fall straight out of this arithmetic, and they are worth pausing on. This figure shows the same boosting run on the ice cream data. Both group predictions start at the overall mean of 60, and with a learning rate of 0.5, have the remaining gap to their true levels of 20 and 100 on every round. Now scale this picture up from 6 points to thousands and from one stump to hundreds of small trees, and you have the engine inside XGBoost. XGBoost is a highly optimized implementation of gradient boosting. Beyond the plain algorithm, it adds a set of practical refinements that make it both faster and more accurate. Those refinements include built-in regularization to combat overfitting, highly efficient parallelized computation, native handling of missing values, smart tree pruning strategies, and flexible objective functions for many kinds of problems. Because of these strengths, you will find XGBoost across business analytics, finance, risk modeling, marketing, and fraud detection. On tabular data, it is often the method to beat. Let us compare bagging and boosting directly. Both are ensembles, but they pursue different goals in different ways. This table sets bagging and boosting side by side at a glance, so the contrast between parallel, variance-reducing trees and sequential, error-correcting trees is easy to see. A useful rule of thumb: random forests make a strong, low-effort default, while XGBoost can squeeze out extra accuracy if you are willing to invest in careful tuning. Stepping back, the three tree-based methods of these two chapters form a natural ladder of capability and cost from the single tree up through the forest to XGBoost. This table compares the tree-based methods directly, lining up decision trees, random forests, and XGBoost on interpretability, accuracy, and the effort each one demands. Here is the key point. A sensible workflow climbs the ladder one rung at a time. Start with a single tree for an interpretable baseline. Move to a random forest for stronger, steadier predictions with little tuning, and reach for XGBoost when you need the last few points of accuracy. Random forests have earned their reputation as a reliable default. They offer strong performance across many problems, far more stability than a single tree, natural handling of nonlinear relationships and feature interactions, little need for scaling, and useful feature importance estimates. They also work for both classification and regression. Their limitations are mostly the price of combining many trees. They are less interpretable, can be computationally heavy, their feature importance can mislead, and they may lag specialized methods on very sparse, high-dimensional data. And like any model, random forests still demand careful validation before you trust their predictions. XGBoost takes a different bargain. It trades simplicity for raw performance. On the plus side, XGBoost often delivers the highest predictive accuracy on tabular data, includes built-in regularization to limit overfitting, handles missing values practically, is flexible and efficient, and works for both classification and regression. On the other side of the ledger, XGBoost is more complex than a random forest, has more hyperparameters to tune, is less interpretable than simple models, can overfit if tuned carelessly, and truly rewards genuine expertise to reach its best. Powerful as it is, XGBoost should never be deployed blindly. Its accuracy is no substitute for understanding and validating what it does. Now let us put this into practice. For a realistic modern classification task, we use the adult dataset, also called census income, which loads directly from OpenML. This code loads the census income data, builds numeric indicator columns from the categorical features, splits the data into training and test sets, and then sets up a random forest classifier ready for training. In plain terms, the code loads the data as a data frame, turns the categorical columns into numeric indicators, and trains a forest of 200 trees using all of the available CPU cores to speed things up. Once the forest is fitted, it can tell us which features it leaned on most for its predictions. This short snippet pulls the importance score for each feature out of the trained forest, sorts the features from most to least important, and prints the top 10. Read that result as a model-based measure of usefulness, not as proof of causality. A high score means the feature helped the model, not that it causes the outcome. Next, we try XGBoost on the same task. Because XGBoost is not part of scikit-learn, you install it first with a quick pip install. This code imports the XGBoost classifier, reuses the same census training and test sets, configures the model with a chosen number of trees, learning rate, depth, and sampling fractions, then fits it and prints accuracy, precision, recall, and the F1 score. In plain terms, those parameters set the number of trees, the learning rate, the depth of each shallow tree, and the fraction of rows and columns each tree gets to see. Tree ensembles handle regression just as well as classification, so let us switch to a regression problem next. This code loads the California housing dataset, splits it into training and test sets, trains a random forest regressor with 200 trees, and then computes error measures to judge how close its predictions are. When you run it, compare these numbers with the single regression tree from Chapter 9 on the same data, and you will see the ensemble's advantage clearly. Our case study turns to credit risk. A lender wants to predict which applicants are likely to default using familiar features like credit score, income, debt-to-income ratio, and prior default history. The stakes are high, both financially for the lender and personally for the applicants. This is a textbook case for climbing the ensemble ladder, but credit risk is exactly where more accurate must not be confused with better. The through line of the case study is the through line of the chapter. Ensembles are powerful, and that power is precisely why they must be used responsibly. The following code loads the German credit dataset from OpenML, encodes its categorical columns, and compares 3 classifiers by their AUC ROC score, so the progression from a single tree to full ensembles is immediately visible. Here the code prepares the German credit data, label encodes each categorical column, splits the data with stratification, and sets up 3 classifiers, a shallow decision tree, a random forest, and gradient boosting to be compared head-to-head. The resulting AUC table makes the accuracy progression concrete. The random forest typically improves on the single tree, and gradient boosting often improves further still. To summarize, ensemble learning combines many models into one stronger, steadier predictor, exploiting the fact that diverse models make different errors that cancel when pooled. Random forests make a robust, low-tuning default, while XGBoost reaches higher accuracy at the cost of careful tuning. To go further, look at introductory treatments of ensemble learning. The scikit-learn documentation on the random forest classes, the XGBoost documentation, and the original gradient boosting literature, and applied case studies on credit risk, fraud detection, and tabular machine learning. That brings us to the end of Chapter 10 on random forests, XGBoost, and ensemble learning, where we saw how pooling many simple models builds one powerful predictor.